All right, let's go ahead and add to our list of chemical reactions. I have a few more for you here. There are a couple more, actually. One of them is the same as last time. This one is new. Reaction between metals and hydrogen to form hydrides. So remember, hydrogen can form an anion by gaining an electron. And we call the anion of hydrogen H minus. Hydride is the name of that ion. So let's take a look at some examples. So metals will react with hydrogen in a synthesis reaction. So sodium metal reacts with hydrogen gas to make sodium hydride. So this is a pretty basic synthesis reaction. Potassium would react with hydrogen the same way to make potassium hydride. Let's look at an alkaline earth metal, say calcium. So again, we just have a synthesis of a binary ionic compound. So we get calcium hydride. Pretty simple. So just know that metals can react with hydrogen to form hydrides, they are called. All right, so here's where it gets a little bit tricky. So ionic hydrides will react with water to form basic solutions. So kind of like the reaction with metal oxides, but it's a little bit different, so be careful. This time we're going to have two products. So metal hydride, this metal being lithium. Lithium hydride reacts with water to produce a basic solution. So you're going to make a base, lithium hydroxide. But this time we have another product. This reaction will always produce hydrogen gas. And for time's sake, I will let you include states of matter and balance that equation so you can take care of that. Here's another example. Calcium hydride reacts with water to produce, again, a basic solution. This time our base is calcium hydroxide. And again, we have hydrogen gas that is produced. So again, be careful with the ionic, net ionic equations for these reactions. Those hydrides are solids. They react with water to produce solutions of those bases. Those are strong bases in these examples, so those would be shown as dissociated in your ionic and net ionic equations. If you take a look on page 235, there's some more examples. We have hydrogen reacting with iodine. So this time that's going to produce a molecular compound. So we just focused previously on reactions between metals and hydrogen to produce ionic compounds. Hydrogen can react with other nonmetals to produce molecular compounds. So again, that's just a synthesis reaction. You'd make hydrogen iodide, HI. That's hydroiodic acid when it's in water, but if there's no water, it just makes hydrogen iodide, which is a gas. Potassium reacts with hydrogen to make a hydride. That would be potassium hydride. And then letter C shows an example of a metal hydride, alkali metal hydride, in this case sodium hydride of water, that produces sodium hydroxide along with hydrogen gas. Example 6-7 asks about the ionic or molecular character. So if it's an ionic compound, it has ionic character. If it's a molecular compound, then it has molecular character. We saw last unit some reactions with oxygen to form metal oxides, and then those metal oxides can react with water. We'll see those again. First, oxygen exists as two allotropes. So allotropes are different forms of the same element. So the oxygen that we breathe is O2. There's another form of oxygen found higher up in our atmosphere, specifically in the stratosphere, called ozone. So we're going to stick primarily with oxygen, O2 reactions, reactions with oxygen gas or O2. All right, review from last units. Metal oxides react with water. Again, a metal oxide is known as a basic oxide or basic anhydride. The alkali metals will alkali metal oxides will react with water in the equation like this. So instead of specific examples like lithium oxide or sodium oxide or potassium, I'm just going to write M for the metal. And because the alkali metals form +1 ions, it'll always be M2O, so Li2O, Na2O, K2O. So this reaction produces one product. It'll be the metal hydroxide. So we get something like that. Alkaline earth metals. Reaction between an alkaline earth metal oxide and water, again, produces the metal hydroxide. Our metal could be calcium or magnesium or strontium, barium, any of those. The nonmetal oxides, also known as acidic anhydrides or acidic oxides, will react with water to produce an acidic solution. So there's some examples on page 240. We've seen quite a few over the last couple weeks. Remember that thing with the oxidation numbers that's shown as well on page 240. Go to 241. There's some examples there of reactions, more reactions with, first one is nonmetal oxide and water. You should know how to write that one. Letter B is a little bit different. It has arsenic, which is a metalloid that reacts with oxygen. The metalloids will react with nonmetals to form molecular compounds. Go ahead and read the solution there in letter B. It talks about the oxidation states possible for arsenic. So arsenic has 5 valence electrons. 2 of those electrons are in an S sublevel. 3 of them are in a P sublevel. So arsenic can form oxidation states of either +3 or +5. +5 if it is giving away all of those electrons, +3 if it's just for the P electrons. There's some more examples on page 242. This time we got metal oxides reacting with water. And then there's a little different one, letter B. We have a metal oxide reacting with a oxide of sulfur. So that one's a little bit different. Look at the example there and see what happens in that reaction. All right, go ahead and practice. Page 248, number 67, you're just identifying the type of oxide that each is. So it's asking specifically if they are basic anhydrides or basic oxides. And so the only ones that are B and D. And then A, C, and E, those look like nonmetal oxides or acidic oxides, acidic anhydrides. If you need more practice with these types of reactions, go ahead and do number 69 on page 248. We're not going to do that together. If you would like to go over those in class, or if you'd like to check your answers, please let me know. I'll be happy to go over those with you. All right, last one, combustion reactions. So we've talked about combustion reactions before, even as long ago as in Chem 1. We're focused primarily on combustion of hydrocarbons. Not that only hydrocarbons can burn, but it's the most common type of combustion reaction that we deal with in this class. So it says fossil fuels are variable mixtures of hydrocarbons. Hydrocarbons, again, being compounds that contain primarily carbon and hydrogen, that when burned are sources of electrons. So what it's really saying here is that combustion reactions are redox reactions. So far, we've only dealt with situations where you have an excess of oxygen, unlimited amount of oxygen, enough oxygen to completely oxidize the carbon in the hydrocarbon to carbon dioxide. So let's take a look at an example. So the hydrocarbon we'll use for these examples is propane, C3H8. Again, the complete combustion, unlimited amount of oxygen, will completely oxidize the carbon in the hydrocarbon to carbon dioxide. Go ahead and pause the video and balance this equation. So if you have a ratio of at least 5:1 oxygen to propane, you will completely oxidize the hydrocarbon to carbon dioxide. This isn't always the case where you have plenty of oxygen. What if you have a limited amount of oxygen? Not enough to completely oxidize the carbon to carbon dioxide. In this case, you get a slightly different written, but very different product. Instead of making carbon dioxide, you could make a very poisonous gas, carbon monoxide. That's why it's important to make sure that anything that is burning in your house, like your furnace or your stove, has plenty of oxygen so that it's producing carbon dioxide and not carbon monoxide. Go ahead and pause the video and balance this equation. So if you have less than a 5-to-1 ratio, in this case we have 3.5-to-1 ratio, mole ratio of oxygen to propane, you're not going to make carbon dioxide. Instead, you're going to make carbon monoxide. What if you have a very limited amount of oxygen, just enough oxygen to support combustion? Again, you're not going to oxidize that carbon all the way to carbon dioxide or even to carbon monoxide. You get, yet again, a different product. This time you get carbon, soot. If you've ever seen a black smoky fire, that black is carbon that has not been oxidized all the way to carbon monoxide or even carbon dioxide. Once again, go ahead and pause the video and balance this equation. So we have less than 5-to-1 ratio. We have less than 3.5-to-1 ratio. 2-to-1 ratio of oxygen to propane is going to yield carbon as our oxidized product. So just know there's different products possible when you burn a hydrocarbon. Plenty of oxygen, you get CO2. A limited amount of oxygen, you get CO. And very limited amount of oxygen, just enough to support combustion, you get carbon. Sometimes hydrocarbons contain elements other than carbon and hydrogen and oxygen. Sometimes they contain nitrogen. And so if you burn a hydrocarbon that also has nitrogen in it, along with those other products listed before, you'll get NOx, or nitrogen oxides. So it could be nitric oxide, NO, could be nitrogen dioxide, NO2, could be nitrous oxide, N2O. So just know that if your hydrocarbon contains nitrogen, you're going to make some oxide of nitrogen. Likewise, sometimes hydrocarbons contain sulfur, and when you burn a hydrocarbon that has sulfur in it, you'll produce SOx, or oxides of sulfur. That could be sulfur dioxide, could be sulfur trioxide. Both are very bad. In fact, both NOx and SOx are pollutant gases because they will combine with the water in our atmosphere to make acids. And that's where acid rain comes from. We have sulfuric acid, which forms in the reaction between sulfur trioxide gas and water. We get nitric acid that forms in the reaction between nitrogen oxides and water. And so this is where acid rain comes from. That concludes this unit. Thanks for joining.